So we'll get started. Thank you very much, Sasha, for the invitation to give this presentation. I'm Sarah Stamps. My pronouns are she, her, and I'm an associate professor in geophysics at Virginia Tech in the Department of Geosciences. My talk today will be on using GNSS observations to constrain extension rates and intra-rift strain rates along the East African Rift system. Some key collaborators for this piece of work that I'll be presenting are Dr. Ella Faraha Saria from Tanzania, Corne Creamer at the University of Nevada, Reno, Rui Fernandez in Portugal, my former PhD student Tahiri Rajaonarison, and my colleague Gerard Rambalamanana in Madagascar. And I'm going to present essentially two projects today. And for those projects, we've received funding from the Global Earthquake Model, National Geographic, and the National Science Foundation. And then we've received some technical support from UNAVCO for many of the GNSS observations. The photo in the background is a view of the clouds. We're above the clouds, and this is a place in Uganda known as the Rwenzori Mountains, where we have several observations of surface motions. And so this was a photograph from the field a couple of years ago. So today's talk will be brief, but it will have 5 points. I'll give an overview of the East African Rift system. I'll talk about GNSS observations. Then I'll show you the technique that I've used to calculate intra-rift strain rates, and then the technique that I use for extension rates, and provide a brief summary at the end. This photograph is from Madagascar, and it's one of our episodic, also known as campaign GNSS observations in that part of the world. So we'll go through the East African Rift system initially. It is the active divergent plate boundary between the Nubian plate here in the west and the Somalian plate over here in the east. I consider the East African Rift system as a whole, this entire region here that stretches from the intersection of the Red Sea, Gulf of Aden, all the way down to south of South Africa at the Southwest Indian Spreading Ridge down here in the south. And then it also extends quite wide east-west from Eastern Congo all the way across to Eastern Madagascar. So that's the system as a whole. And then the current rates are about 1 to 6 millimeters per year from some work by Saria and myself. And then there's at least 3 minor blocks, the Victoria block, the Rovuma block, and the Lawandle block as well, also known as microplates in my world. And then it is seismically active, as shown by the squares and circles in different colors in this map. And the squares and circles are representing different magnitudes of earthquakes and different depths to give a little bit of perspective in this figure. It's also volcanically active. And then some of my recent work showed that there is this zone of diffuse deformation as these white bars here that I'll talk about later in this presentation. So one thing I did want to point out that a lot of times we'll see East African Rift in the literature, and that tends to be more focused on the continental region of the East African Rift system. But in my view, the system as a whole, the East African Rift system, covers a much broader area than what people tend to identify as the East African Rift. So a little bit about GNSS observations. GNSS stands for Global Navigation Satellite Systems. Currently, there are 6 major GNSS systems. The GPS system, which is the oldest one, operated by the US. There's GLONASS, operated by Russia. Galileo, operated by Europe. Beidou, operated by China. And also QZSS, operated by Japan. And IRNSS, operated by India. This figure to the right shows the orbital paths of those 6 GNSS systems. They all transmit within the L frequency band, but slightly different frequencies. And then they all are also orbiting between 25,000 or up to 40,000 kilometers away from the Earth's surface. And then they all have a control segment with stations on the ground to provide operations to the satellites if needed. They have a user segment, which is like us, scientists or civilians, and then they all have their satellite segment. And then in order to get a position on Earth, you do need 4 satellites. Some people think you only need 3, but you do need 4 in order to get the XYZ coordinates and also time, because you have to solve for the time differential from when the signal left the satellite to when it reached the Earth's surface. And then I was asked to give a little overview, so I just wanted to point out the kind of complicated but simple, if you know it, phase equation. So there's a lot of things that geodesists correct for because the signal travels from the satellite through the ionosphere and the troposphere, and there's a lot of corrections that have to be made. There's also this clock error because the clock in the GNSS receiver is less precise than the clock in the satellite. So there's a lot of corrections that have to be made. And currently these are 3 examples of some research grade software systems: Gamut Globe K, Bernice, Gypsy X. These are all available. One of them costs money. In my group, we use Gamut Globe K, but these all allow us to do these complex corrections and actually get millimeter precision positions and velocities. And I also wanted to point out that there are 2 types of GNSS observations. There's campaign, which is also known as episodic observations. So these are systems that you measure a benchmark that stays fixed, and you'll set up your instruments for a few days or maybe a couple of weeks, and then take your instrument down, and then you come back maybe 6 months later or a year later, remeasure that same benchmark and see how long it moved or how far it moved over the time period between your observations. It takes about 3 to 5 years of repeated observations to get reliable tectonic signals. And then you have continuous observations like this one shown here. This one is in Kenya. So this one you need a minimum of 2.5 years of observations. And so this is where the station consistently stays in the ground, or it stays observing all the time. And there's a paper by Blewett and Lavallee that show you need at least 2.5 years to be able to solve for the seasonal signals. Many of us like to prefer 3 years, but there is a minimum of 2.5 years, according to that work in 2002. Okay, so I'm going to now move into intra-rift strain rates. So this is an approach called the Haynes and Holt method. It was developed in the early 90s and revised to use bicubic vessel splines in the later 90s. It is quite, it's been used many places globally. The global strain rate model, which is pretty popular, that uses this technique. And then many scientists have used it regionally as well. It's not the only way to get intra-rift strain rates, but this is one approach. In this approach, you need velocities, and you invert for strain rates, particularly you solve for the entire velocity gradient tensor, which has 2 components, the strain rate tensor component and the rotation metrics component shown here. So you're able to solve for both strain rates and predict surface velocities as well. And this is a map here from a paper I published in 2018 using this method. The data are shown in blue and also white, and then the red is the predicted velocity. So it's actually a little bit simpler than this equation would suggest, because we don't concern ourselves with the vertical component. You just use the horizontal components. And so the equation reduces, or this matrix reduces just to a 2x2 matrix. So it's computationally pretty easy to do. This map here shows the strain rates for this particular work. Red is extensional strain rates and black is compressional. And as expected, most of East Africa, the East African Rift is extensional. So the steps to using this approach require that you define a finite element grid, which is shown in A, and then you have to make some decisions about where you want to define zones of rigidity versus zones of deformation. And so we used maps of seismicity like shown in B, and then the maps of where we had the data, which could constrain the model. So this particular approach that we used only constrains the model with GNSS data. So then we took this information, we did try several iterations of the block boundaries versus the deformation zones, and we decided upon this configuration. So everything that's in black is deforming. Everything that's not black is considered rigid. So we do the method, and then these are some derivatives that can be determined or calculated from the strain rates. And so in the right is the strain rate magnitude, also known as the second invariant of the strain rate. And then to the left is the dilatation, which shows where it's dominantly compressional or dominantly tensional.
Sarah,
so,
you have 10 minutes now.
Perfect, thank you. So now I'll move into extension rates. So for the extension rates, we've used the approach of McCaffrey 2009, which is TDEFnode. This one is openly available, and I'm providing you the website here. So this is a completely different approach. This one assumes elastic blocks, and you define block regions and you bound them by pseudo faults. And then in the approach I'm going to show you today, we use freely slipping block boundaries. And that's because the velocities in East Africa are quite slow. And we simply invert for the angular velocities based on the GNSS observations. So this is a map of a recent velocity solution that I published in 2020 or 2021, depending on which reference you look at. But in red are stations that have been used previously, but we have extended the time series. In yellow are new stations or new data that has not been used previously. And we did utilize Gamma-GloK for this solution. 16 sites are continuous and originally predicted to be on the Somalian plate. We have 5 episodic sites and 3 continuous sites on Madagascar, and then 1 new site here in the Comoros that we only use data for before the 2018 events. So for this work, we did several experiments, and one of the questions was, does Madagascar move rigidly with the Somalian plate? So is it actually part of the Somalian plate? And when we include the data and do some statistical analysis, it is absolutely no. The entire continental island is not moving with Somalian plate. Then we do several more tests to see if Comoros is moving with the Somalian plate, and no, it isn't. And then we also test each site individually on Madagascar to see if they are consistent with Somalia plate motion. And we find that 3, in fact, are. So this is a geometric interpretation of the data. So the ones that were, and these are residuals also I'm showing here. So the ones that are here, they did fit with rigid Somalia plate motion, and that was also consistent with the low seismicity in that region. So then we had to also question if the southern Madagascar moved with the Lawandle plate. And so we did this approach of Stein and Gordon, where you do an F-test to determine if a model is better fit and significantly significant if it includes more blocks. So we did that approach. And indeed, statistically, we were able to show that, yes, Lawandle is warranted, and we get a much better fit when we include the Lawandle microplate. So to summarize that work very quickly, we have extension rates along the East African Rift system that have been revised. And then we found this broad zone of deformation here. And then this showed that the East African Rift system is extending with both narrow strain accommodation and diffuse deformation. And then we were able to refine the geometries and also the velocities, the angular velocities here for the Lawandle plate and the Somalian plate. So to summarize, I'm going to leave you with these references here of the work that I presented. This is the strain rate model, which is available open access, and it has all of the velocities and strain rates available. And then the extension rates, I made all of the model input and output files open access, and it's published in geology as well. Okay, that's all, I'm finished.
Thanks a lot, Sarah. Very well in time. Do we have questions? If so, please put them in the chat, or if you don't have enough time to write it, then just write Q and you'll get the word. And while you write, I would have a question to kick things off. In the area. Oh, you stopped sharing.
Oh, I'm sorry. I can
Could
share
you
again. Go
continue?
ahead.
You
Sorry,
just had
sorry about
the,
that.
you just had
Okay,
the
yes.
image there that I wanted to ask a question about.
Yes.
On the left side, at the southern tip of the Victoria microplate, this is the region where you have the highest compressional strain rates.
Yeah.
How do you interpret this? Why is this there? What do you think?
Yeah, this is where we have the Rukwa Rift and the Tanganyika Rift over here, and then the intersection with the Malawi Rift. And there is some transform motion that occurs in this area as well. It is consistent with the combination of strike slip faulting and extensional faulting that we see in this area. And Chris may want to say something more to this as well. But we also predicted the style of faulting that's expected. That's another thing that you can extract from these types of models. And it was both strike slip motions and extensional. So to me, it's the combination of both the compression in the black and the extension in the right indicates there's strike slip motion happening, which we do see in that area.
Okay, thanks. Any other questions? Sam has a question. It's a long one. You have to ask it yourself for sure.
Okay, I can see it in the chat. So Sam says, you have one measurement on the Comoras, Mayotte, I assume. What is the effect on the accuracy overall of your modeling? And would more stations there potentially provide a major impact on your interpretations? It is Mayotte, yes. And what is the accuracy effect on your overall modeling? Well, we did some tests with and without Mayotte. So statistically, like, we did our best to account for that. It is only one station. It was pretty well resolved. And then let's see. If we had more stations right in this area, I mean, we'd have to just do the test to see how they affect it. But if they're all clustered in one area and they all move in the same direction, it wouldn't really change the results. And okay, and then a question from Cecile is the same idea. Do you know any compressional earthquakes in southern Madagascar? The motion of individual Luanda plate seems to be based on few data. There actually are a couple of compressional events in southern Madagascar. So Sasha, we're at 10:20. I don't know if we should switch or if we should just keep fielding questions.
I was about to jump in.